Welcome to this explainer. Today, we're diving into a real scientific whodunit. Section 7.3, How is periodicity extracted? Have you ever stopped to wonder how exactly your auditory system pulls pitch out of a complex soup of sound waves? It's wild. We're going to explore the hidden mechanisms your brain uses to turn just raw physical frequencies into the melodies you're actually hearing right now.
So, think about this for a second. If the absolute foundation of a sound is missing, how does your brain still build the house? It's this incredible perceptual mystery. If you literally strip away the main fundamental frequency of a sound, you still miraculously hear its pitch. Your brain essentially just fills in the blank. But how on earth does it do that? To solve this, here's our roadmap. First, how is periodicity extracted? Then we'll look at the missing fundamental and dominant region. After that, we'll interrogate our two main suspects, pattern recognition and temporal models. And finally, we'll search for clues in the neural mechanisms themselves. Let's get into it.
Section 7.3.1, The Missing Fundamental and the Dominant Region, Establishing the Illusion. We're starting our investigation with a really famous auditory illusion, one that actually proved the early acoustic pioneers completely wrong. They assumed we just extracted the lowest frequency we heard, but wow, our brains are way more clever than that.
The truly crucial breakthrough here came in 1956 from a researcher named J.C.R. Licklider. He proved something amazing. Your perception of pitch remains entirely unchanged, even if the fundamental frequency is completely masked by noise. Meaning, your brain isn't just lazily relying on the lowest frequency to hear pitch, it actually extracts it from the higher harmonics. It's kind of like reading a word with the first letter missing. You still instantly know what the word is, right? What researchers discovered next is that certain low-numbered harmonics completely dominate what we hear. If you mistune just the second, third, or fourth harmonic by a tiny margin, like, say, just 3%, it heavily shifts the entire pitch you perceive. It absolutely proves that our brain weighs these specific, resolved harmonics super heavily when it's calculating the overall pitch.
Now, a quick side note, basically a warning for any future scientists out there. If you're setting up an experiment to remove these lower frequencies, you absolutely have to use low-pass masking noise. Why? Well, the human ear is highly nonlinear, which means it creates its own internal distortion. If you don't mask it, your own ear will literally generate a fake fundamental frequency right inside your head as a combination tone. And yeah, that completely ruins the experiment.
All right, moving on to Section 7.3.2, Pattern Recognition, Suspect Number 1. Let's see how this incredible illusion builds the foundation for our first major theory on how the brain pulls this off.
Suspect number 1 is a theory based on a concept called the harmonic template. The idea here is that your brain matches incoming, resolved harmonic frequencies to pre-existing templates stored right there in your memory. You can think of this model kind of like finding a precisely cut stencil, or maybe a puzzle piece that perfectly fits a specific set of frequency dots.
For instance, imagine incoming harmonics at 300, 400, and 500 Hz. They slot perfectly into a 100 Hz template. So even though the 100 Hz and 200 Hz tones are completely missing from the actual sound hitting your ear, the spacing of those higher harmonics matches the 100 Hz stencil the best. Your brain finds that best fit, and boom, you instantly hear a 100 Hz pitch.
But our first suspect has a massive flaw. The big issue, the alibi if you will, is that pattern recognition entirely fails to explain how we hear pitch from unresolved harmonics. You know, those high, tightly clustered frequencies, or from modulated noise. In those scenarios, there aren't any clearly defined individual frequencies to comfortably slot into a template, yet human beings still clearly hear musical pitch. So, pattern recognition, it just can't be the whole story.
Which leads us perfectly into Section 7.3.3, Temporal Models, Suspect Number 2. Since we desperately need a mechanism that can handle both resolved and unresolved harmonics, we bring in our next major theory.
This second suspect relies heavily on something called autocorrelation. Now, this is a mathematical process of measuring periodicity by taking a neural signal and correlating it with a delayed representation of itself. I know that sounds complicated, but just imagine taking a piece of pattern fabric, making a duplicate of it, and then sliding that copy over the original until the patterns perfectly align. The exact moment they align, you found the repetition rate.
The way this works in theory is that time delays matching the original pulse period result in incredibly strong correlation spikes. Basically, you take the original neural spikes, delay them by different time intervals,
And wherever they overlap the absolute strongest, that interval is your fundamental pitch. It's a really elegant mathematical solution, especially because it easily handles both resolved harmonics in the messy, clustered envelopes of unresolved ones.
So, the crux of this theory is a surprisingly simple three-step process. 1. Take the original neural signal. 2. Delay it by different time intervals. And 3. Multiply and sum those signals to find the strongest correlation. The auditory system theoretically uses this single mechanism to grab timing information across radically different frequency channels, mashing it all together into one unified sensation of pitch.
Now, if we step back and compare our two theoretical suspects directly, here's what we get. Pattern recognition excels with resolved harmonics, but absolutely fails with unresolved ones. Temporal models, on the flip side, can explain both, but they really struggle to account for why resolved harmonics produce such a vastly stronger, clearer pitch than unresolved ones do. So both theories are honestly brilliant, yet both leave us with some pretty glaring scientific plot holes.
So, where do we go from here? Well, Section 7.3.4, Neural Mechanisms, the Crime Scene Investigation. To truly solve this mystery and figure out which algorithm the brain is actually running, we have to look directly at the physical hardware, the brain itself.
We literally track the neural signal up the auditory pathway, and we're looking for what scientists call a periodotopic organization. Basically, a place where neurons are specifically tuned to pitch periodicities. This search takes us from the postcochlear nucleus up through the medial geniculate body where, interestingly enough, the phase locking limit drops to about 800 Hz, then up to the inferior colliculus, and finally right into the auditory cortex.
And along this pathway, researchers found some unbelievable clues. In a major breakthrough, they discovered pitch-selective neurons right in the auditory cortex of marmoset monkeys. These highly specific neurons fire strongly in response to a specific fundamental frequency, completely regardless of whether the sound contains only high or only low harmonics. It's a massive piece of the puzzle. But what about us? Well, human brain imaging shows huge hyperactivity in specific cortical regions whenever a pitch is heard, specifically near the lateral Heschkel's gyrus and an area called the planum temporale. But, and here's the really tricky part, whether this region is the actual extraction site doing all the mathematical heavy lifting, or if it's just the place receiving the final fully processed pitch signal from deeper in the brainstem, that is still hotly debated.
Which brings us right back around to our suspect theories, particularly the temporal model. Frustratingly, we're dealing with a missing weapons scenario here. There's almost zero conclusive physical evidence for the biological neural delay lines that are required to make autocorrelation actually work. For that theory to be strictly true, we need physical pathways in the brain that delay signals perfectly. And so far, the anatomical evidence is just incredibly scarce.
The source material actually sums this up perfectly, stating, "We see several tantalizing glimpses of neural pitch mechanisms, but nothing we can be sure of at present. We know exactly what the auditory system achieves. I mean, it's nothing short of a biological miracle. But the ultimate algorithm it uses to do it, that remains an incredibly elusive puzzle."
I want to leave you with this final thought. As you sit there, listening to the pitch of my voice right now, where exactly in your brain is that invisible conductor extracting that pitch? A completely hidden, massively complex algorithm in your mind is actively constructing the musical reality you're perceiving this very second, and we are only just beginning to understand how. Thanks so much for joining me on this explainer. Keep asking those big questions, and I'll catch you in the next one.